All right, thanks for sticking around in the pool. So I'm going to present to you an introduction to X-ROM, which is X-ray reconstruction of moving morphology. And I'll be talking about kind of the kinematic and some of the basics of our equipment, and then Dave Lee will follow up with some information about how you get inverse dynamics and force and moment measurements out of this system. So I just want to mention real fast, first off, that this is a big project, so it's a big collaboration between the department I'm in, which is ecology and evolutionary biology, as well as some of the orthopedics guys at Brown, some of the engineering and CS guys, and we've kind of all come together to create this workflow that allows us to examine skeletal kinematics. So I told you what it means, X-ray reconstruction, moving morphology, but what does that mean? It means we get a 3D imaging of skeletal motion. This is 6 degree of freedom motion of the bones. We've got three translations and 3 rotations of every element that we're analyzing, and we're doing this by getting high quality kinematics from biplanar X-ray video. So we have 2 X-ray machines that we're recording high-speed video from, and then we're combining those with high detail models from CTs or laser scanning or potentially MRI. So why use X-ROM? We all know you can go get a motion capture system and just use that, and they're relatively cheap these days. And the answer is that that's great for certain types of questions, but certain types of research questions, specifically like what's happening at a joint, say, how are 2 bones interacting in detail, you can't necessarily get that from motion capture. You've got skin waggle, muscles are bulging, all those elements of soft tissues that they do makes it hard to track what's going on with the bones that are underneath all that. So we did not have the idea that biplanar X-ray might be a great way to approach this. In fact, the orthopedists were ahead of us by about 10 years in realizing that this might be a great way to take a look at actual skeletal motion. So Tashman and Anders and their colleagues realized that with 2 X-rays, you've got this overlapping volume, you can calibrate that 3D space somehow, and then you can get 3D kinematics out of that. So they were orthopedists, but these guys they're using a dog there to run the system. They called it dynamic RSA, which stands for Roentgen photogrammetric analysis. I think X-ROM slightly rolls off a little bit easier. But they've got overlapping X-ray videos. What they do is they stick these tantalum markers in, so that's these dark spots on these bones here. They track those kinematics. They combine those with CT scans of the bones, and then they drive those bone models according to the kinematics that they got from these markers. So that's basically the same. We realized that seems like a great idea. We're interested in comparative zoology. The orthopedic guys are interested in taking a look at joints of humans. It just seemed like a great idea, so we wanted to develop both systems to gather these data as well as a general workflow that a variety of people could use to analyze motion data. Yep. Right where? That, I was actually wondering the same thing when I just saw that. My guess is, it might be, I don't know, Tom, if you know this paper, this might be some kind of disease process or something like that. If you get,
yeah, or maybe the model's just a little off. I don't know. It doesn't look.
I feel like the knee, the femoral condyles, you sometimes get funky, kind of calcified stuff going on. Could be some of that too.
They got the anterior cruciate ligament.
Oh, do they? Oh, that's cool.
That's on Church.
Okay, so that might be something that relates to, they were looking at the ACL. David says that might also relate to something they're examining there. So what we did is initially we set up this system using retrofitted medical C-arms, and when we were happy with that, we got a bigger grant, and we constructed this bigger tech foundation facility. And so I'll introduce you to the C-arms and kind of how they work generally, and then I'll talk about why we then moved on and constructed this bigger facility. So,
Can you just talk about money a little bit?
I can talk about money on the next slide. Is that cool? So I just want to show you kind of how the C-arms are working. So there's an X-ray source here, there's an X-ray source over here off camera, and then these are each, this is a terrible one. You were right, Tom. These are image intensifiers here, which are going to grab the X-rays, and then they're going to be backed by high-speed cameras. I don't know why that didn't move. And then you'll see once this plays again. All right, maybe you won't see. There we go. And you'll see once we start up the X-rays, we're going to be getting the two views back here. So in this case, they're taking a look at this pig feeding. So the C-arms. The C-arms together, I think including the image intensifier addition, we bulked up the size of those so that we could get a bigger imaging volume. Ran about $140,000 US dollars, and then high-speed video cameras were about $20,000, or sorry, about $30,000 each. So winds up bringing this system to about $200,000 total. We've got something about the size of a soccer ball. These two systems will overlap. That's about the volume you can get. The voltages and intensities that you can get out of these X-rays are pretty good for anything that's really terrestrial. One reason we ended up going to a bigger, more powerful system is because we have people interested in fish and things like that, which are in water, but we're just shooting through air here besides flesh. And we can go up to about 1,000 frames per second with these guys, and about 30 seconds of continuous operation. So some of the benefits of this is that compared to certain systems, it's, depending on your point of view, it's relatively inexpensive considering we're generating X-rays, we're getting these 3D data out. We've got very good accuracy and precision. And one of the other reasons that this system is relatively cheap is because the X-ray source and the image intensifiers are locked into position. You don't need to have a special room for this. You don't need to shield it because you're capturing all the X-rays. You get a little bit of backscatter. That's why we wear lead protection and things like that. But the room itself, center blocks and things like that are sufficient to shield it. And it's relatively simple to configure because of that, because it's always pointing in the right direction. Everything is kind of happy. Some of the disadvantages are, again, it's not a huge overlapping volume. The energies, I think, are pretty good for terrestrial locomotion, but if you want to study fish or study sediment or substrate, things like that, you might want more power. And then these C-arms themselves, which lock you into position and make them easy to use and let you use this unshielded room, also can get in the way if you're trying to configure and get certain views sometimes. So it's just kind of a physical, sometimes there are certain views you would want that are physically not possible with this system. So those disadvantages are why we expanded and built this PIC Foundation facility. And so now we've got image intensifiers and high-speed X-rays mounted on these carts that are physically separate from the X-ray sources, which are mounted on these sleds from the ceiling. So now we have a lot more flexibility in types of setups we can do. So we can do a very simple setup like this that the C-arms might allow us to do. But we can also do some of these more interesting setups that the C-arms just wouldn't allow us to get to.
Sure. Now, you said, can you do what is exactly, can use the X-ray sources like this to get using the stereo uses
So the question is whether we could set them up close enough to each other that we could get 3D stereo views. And that's an interesting question. I'm not sure. There's still a limit to how close you can get these guys because they have various housing that houses the So now that we have a separate sled with the image intensifier, we need to be able to, we have lead iris that we can open it closed so that we're not shooting X-ray off of the intensifier. So that housing, the kind of the tilt housing and things like that. So these guys have a lot of axes of rotation that they can go on, but there's a housing for the motors that are driving that. And then I think there's also just the actual, the magnets that are actually focusing the beam all in there. So they're a little bit bigger and clunkier. I'm not sure whether. Yes, so you could do a virtual type of thing like that. That is true. But for actually having the two X-ray views right next to each other, I'm not sure. There's definitely some kind of physical limit still.
It would be a little bit rough. You basically have a cone of photons coming to those intensifiers. You want to keep your subject as close to the intensifier as possible, maximize the volume where the cones intersect.
Okay.
And that's what your 3D volume is.
Oh, I see. Sure. So you want closer or far?
Well, the best, so it sort of depends. So actually for the guinea fowl stuff, we have them relatively orthogonal, but sometimes like if you end up with more of that diamond shape, one advantage is in a certain plane, you'll get a little bit more length out of it, but you're going to be contracting yourself mediolaterally, say. And so it's always going to be a trade-off, but David's right that the maximum volume is always going to be having your image intensifier very close to your subject, because that's just, that's the biggest part of the cone. So now with this facility, we've got this more flexible configuration. We've got a larger, so these have larger image intensifiers. We can image a bigger volumes, basketball size, say, compared to the soccer size with the C-arms. We've got higher energies. So I mentioned that was particularly interesting for people who want to do aquatic type things or maybe things with sediment, but also you can also amp up power to try and reduce your noise as well. So it's nice to have the option. These guys are also able to do pulse or continuous X-ray generation, and if you can do pulse, that means you're giving a lower dose, you can run for longer, so that's potentially an advantage. We're doing human subjects, which the orthopedics guys do things with, say, wrist motion, somebody's taking a look at cutting maneuvers and trying to figure out ACL strains and things like that, so they can have someone hop through this beam and they're not getting such a high dose that they're not able to get IRB. So one or two concerns or things to keep in mind for doing this type of work. One is that X-rays are somewhat sensitive to electromagnetic fields, which can induce distortion. The image intensifiers themselves have a shape that introduces distortion, so you don't get, it's not just like, I mean, light video has some parallax, but these things can get really screwed up. Luckily, we've got, the CS guys put together a routine in MATLAB, so a lot of this workflow happens in MATLAB, the digitizing, things like this de-distortion, so that we've got this grid you can just order right from McMaster's. You run it through this MATLAB program, and it comes up with a lookup table that'll de-distort this image, and then you can just apply that to all your X-ray videos, so you get an undistorted X-ray image. Yes, I will give you the place that you can get all of this at the end. Absolutely. Another concern, although it's kind of a good concern these days, is that we now have multiple ways to track bones. So in the data that Steve and I have been showing at this conference, we use the sort of attachment approach where we have radiopaque markers. In this case, we're actually using these carbide markers, but if you see where it's slightly darker on some of these bones, those are our markers. That's probably hard for you to see, so I'll highlight them, and then now we can pop back, and hopefully that makes them stand out a little bit better in these images. So we are surgically implanting these because you want them to stay rigid relative to the bones, because what we end up doing is we then sacrifice this animal, put it in a CT scanner, get how those how the markers relate to the bones, and then we digitize the positions of those markers, and those markers drive the bones via rigid body calculation. Now, there are, yeah?
Can submicrometry crystals be used as markers and get those 2 points of data simultaneously?
I have not taken a look, David. Do you know how radiopaque sonomicrometry markers end up looking? I'm not, I think that could potentially be done, but I'm not sure. Okay, so David's saying he's guessing they're significantly less dense than some of this metal, in which case it might work on something that's small that you didn't have a lot of soft tissue to work through, but you really want the density contrast between the soft tissue. And it's going to depend on where, if you're out on the metatarsus and it's away from the body, you might have more luck. If you're up like at the hip or something like that and you have to pass through a lot of soft tissue, you might run into problems with just being able to tell it apart from everything else. So we have the knee tends to get a little bit lucky in our birds, particularly sometimes. We do have non-marker approaches. One of these approaches is the ones the orthopedists are using, which is this computerized auto tracking. So what they do is they take this CT, they segment out the bone they want, and then the computer uses a variety of edge matching algorithms and things like that to actually match it to both X-ray views simultaneously. They've had a lot of success with doing this for the knee in the human. We tried it, we had less success. You'd probably notice that our X-rays got a little murky up near the knee, particularly places like that. That's where the really interesting geometry is that gives you, say, like long axis rotation. So it could fit like the shaft, but then the bone would just kind of trundle up and down. So it kind of depends if you have enough surface morphology to give you the good fit or not. Again, the orthopedists are having good success with this, and potentially there's animal models that could work well for this. Another thing you can do, if this isn't working for you, let's say your organism is too small to implant markers or too delicate or something like that, is that you can basically do what the computer's doing by hand, and we're calling that scientific rotoscoping. There's a paper I'll have a source for on how to do that. And there are ways to make it a little easier on yourself. You can reduce degrees of freedom you don't think are important. You can put together a marionette that kind of has elements linked so that you can work proximally, and then the distal things are kind of closer to where their position should be based on your knowledge of the anatomy. So there are ways to make that a little easier on yourself. But those are both two methods for trying to track this motion without having to implant markers. So what do we get? We get, this is that pig feeding, so we've got the two x-ray views, and then in this case we're using the marker-based X-ROM, and then we drive these bone models according to that. So we get what this pig was actually doing, which is nice. It's the same trial. You don't have to be looking at two different trials and trying to infer things. That's how the bones were actually moving. That was slowed down. You can also get information on, not happening. It should play in real time, which is kind of fun to see because they're super chattery compared to looks like it's just hanging out. These are moving very quickly, but you can do things like slow down, speed up, do anything you want to once you have this animation in place. So Greg wanted me to mention some things about assumptions and limitations of these methods. The only assumption I could think of that was particularly important was that the bones are rigid. So if they're marked, then any bone model you have attached to that rigidly moves. In rotoscoping right now, there's not really a way to deform a bone. So if you thought a bone was moving, was big enough, I think you would want to mark different portions of it and treat them as separate bones, and then see whether the rotations and translations you came up with kept those. If they all wound up in alignment, I guess you would be finding that there wasn't deformation. Then if you had this, the bone was slicing through itself, then you would be feeling like there was some kind of bending or other distortion going on. Size is an issue, so you can't do, so we're doing guinea fowl, we can do a whole limb. If you want to do a human, you can't do a whole limb, right? You've only got basketball, you can do a joint at a time, you've got to have the motion occur within that volume. Size of the organism can be, at the opposite end, could be an issue. If you have something too small to implant markers into, you've got to go markerless, so there might be some issues there. The radiation dose for human subjects is potentially a concern. I would be really surprised if you could do anything for T-roll right now because you're just going to be shooting through the guts. Extremities are pretty resistant to radiation. They don't worry about them as much. These guys, the soft organs are more sensitive to radiation. You'd really have to hit them with higher energies to be able to see the bones well. So I just think there's some things that this is not really going to work for right now. And then also, if you want to use the marker approach, you're going to have to do some surgery. Things are going to get a little funky. So if any of this sounds interesting, there are facilities that are either up and running or planned all over the place. These ones on the right are more for orthopedics and human-centered. These ones on the left are more comparative zoology and animal-centered. But of course, I mentioned at Brown we do both, and so you could potentially do both at lots of these places, although some of the hospitals might not want you bringing in animals. That's always a concern.
So if you know they have to like
Yep.
last year they have and then are some displays available to be studied, and also do we have resources where we can take a film of a live oxygen wild, for example, that usually by hand or
So there's, I don't know how much David's going to talk about it, but he's on a big research coordination grant, the goal of which is to create a central database where we're going to have these data, and hopefully the idea is to publish on what you have, and then at some point you kind of allow more access, and people kind of request access to your data if they want to look at something really different, so So potentially there's, we're trying to make it easier for people to share data, because, you know, I'm studying hind limbs. If you can see the sternum, you might be interested in breathing or something like that, and to make it easier to share that type of information. So we're trying to put things in place to make that feasible. It's not too big of an issue these days with hard drives. Just one thing says these are big. You know, we're taking gigabytes of movies easily every day for trials. So the first place you want to go if you want some more information is xarm.org. Because that is a lot of links. It should have the information on these two papers, which are where the actual journal articles where both XROM in general, the workflow, and the scientific rotoscoping are described. This is also a good one if you're curious about estimating accuracy and precision. This Miranda et al. Paper. There's also a Miranda et al. Abstract that I can send you the information for. You can look up yourself, which has some information on accuracy and precision with number of markers. Not surprisingly, the more markers you put in, those both get. And with that, I'll take any questions. I think I'm almost out of time. Yeah.
Has anybody made a beautiful movie like you showed of the pig's jaw of a human knee?
That's an interesting question, whether Danny has any good movies or not. I don't know. It's a good question. Yeah, back there.
Have you considered actuating the scanner and the back plates so you can increase your effective volume?
So the question was whether we had considered actuating the scanner and the back so that we could get more volume. I think that my guess is that now this has been out in orthopedics for a while. That's the next place that they're going to go, is starting to have a mobile, track the knee through a couple of strides or something like that. And I think some of those orthopedists are already thinking about it. Right now, this is pretty new for us. Our system is giving us all kinds of detail that we haven't been able to get before, so we're happy with it. But yeah, I think the human people are going to move there sooner rather than later, probably.
Question?
Yep.
So in the computer animation business, they are interested in using surface skin features, lots and lots of markers, to try to guesstimate where, for example, the shoulder bones are and stuff like that.
Right.
It's conceivable you can do that on an animal for a while, then do this to sort of provide more information or validate or whatever, and thus be able to estimate bone positions in field studies rather than always in the neighborhood.
Yeah, so the question was talking about kind of how Hollywood rotoscopers are trying to use a lot of markers to try and estimate where where the skeleton is, and if we could integrate that with our data and eventually come up with, I think, with some kind of model that would relate those two in some kind of certain way. I think that is potentially doable, and I think it would be, there are definitely tasks that would be easier on, tasks that would be harder on, but right now we don't have those animal data yet. That's been so this is basically, we're just starting to make this jump from, all right, people have been doing kind of 3D segment kinematics where you're connecting the two joint centers with a stick, but we're now just starting to understand, okay, what kind of rotations are really going on, which ones are important, and things like that. And so I think that is potentially, that definitely could potentially be done. I think it would be harder in some organisms, easier in others. But some questions just will never be, if you really want to know how joints interact and what's going on at the surfaces, things like that, I think that there's not really going to be a good replacement for the X-ray data. So, yep.
Chris, that question, I looked at some aspects of that. It also not just depends on taxa, but where on the organism you're trying to model the skin from. So, like the face in humans is a fairly tight skinned area, which can reflect some movement. But you get down in the torso, and the variation in movement of organs and skin versus the bones becomes, the error and the variability becomes huge between individuals. So I guess what I'm saying is, for some places, yeah, it would work. In other places, probably not.
Right. In this session, we've seen sort of new technologies. For example, we can do ultrasound motion capture in addition to tracking visible markers. And now you're tracking internal features like bone prominences and stuff like that. So it's not as hopeless as it sounds.
True.
Maybe last
Anything
question.
else, real quick? Yeah.
What's the limit on the velocity of motions that you can capture when you're doing these scans?
So we can capture up to 1,000 frames per second with both these systems. And then it's going to a little bit depend on if you can get the energy to be shooting through however much tissue or material there is to shoot through that gives you a clear enough image given your not focal length, not frame rate, but given your shutter speed, exposure time. So there's going to be a little bit of play out there, but conceivably, everything that we've been doing, if you can get enough energy through that you get exposed, then 1,000 frames per second, if the behavior happens within that
Yeah,
time.
it comes down to putting out enough light without washing out your subject. certainly, if you've got lots of money, you could buy much faster digital, because these are just high-speed digital cameras we couple to the X-ray, analog X-ray intensifiers. As Robert said, it's limited by light, by photons.
Well, let's thank Robert for. And David Lee will finish up this tutorial with about a 20-minute talk.
While he's plugging in, can I ask a question to the audience? Are the people who, we talked about inverse dynamics, and then this is, I guess, asking Chris's question. Is there a whole community of people who does body motion with soft tissue, with dynamics of muscles? Is that a research area, or people work on that, or not?
Pay's lab at UBC, I guess.
Where you do inverse dynamics coupled with finite element information of the soft tissue.
The closest thing I can.
people are doing it.
Yeah, I'd say look at Hollywood.
All right, well, it's quite late in the meeting at this point. And so Robert's done an excellent job of introducing X-ray techniques. And I think the best thing that I can do is provide, sort of put it in context of dynamic analysis, which is what we're all really interested in. And so I'm going to go through this, and as Robert spoke, I tried to cut out all the redundant slides. And so I hope I may zoom through some things, and I hope you'll stop me if anything, if you want anything clarified. Computed tomography, and so I'll try to start with my overview. What we're really interested in with the X-ray techniques is getting 3D kinematics. I like to start off by talking about 3D X-ray motion analysis, just by analogy to human retroreflective or visual light-based techniques. So really, the first thing we're doing is getting kinematics using X-rays instead of typical retroreflective setups. The other information we need to do dynamics, at least fully, some information about the 3D structure and the 3D, of course, 3D kinetics. If we have a force plate or other transducer, that can give us an idea of what kind of forces are acting on the system. So XRUM, as you've seen, combines a detailed anatomical geometrical model of the bone with the 3D kinematics that we can get from an X-ray system. And the dynamics use a lot of the same information. And of course, we have to add things like we have to figure out as best we can the inertial properties of each segment in order to do ultimately to do the dynamics. And of course, add the force measurements we can get in the experiment. What? Oh, particle image velocimetry. That's a way to estimate forces in fluid. Velocimetry. It's a way to estimate forces in fluids. I just put that in for completeness to try to be as general as possible. So the issue of price came up. So my system was actually assembled by some non-destructive testing engineers, industrial engineers in the Bay Area, and it's like the Millennium Falcon. These are of all the large format X-ray systems we have for comparative biomechanics. This is the cheap one that's just barely holding together. The one in Vienna is millions of euros, as I understand it. And so, if you want to talk to me about cheap stuff for large format, this is about as cheap as I think you can get for large format systems. And of course, I have to acknowledge Beth in particular about trying to make the most affordable system. My estimate's a little lower than Robert's, but the idea of taking refurbished C-arm, medical C-arm X-rays and putting together that $150,000, that's 11-inch intensifier versus a 16-inch intensifier. So if you're doing smaller subjects, you can get away with a cheaper system.
Is there an issue with test subjects in medical versus industrial?
Oh yeah. Yeah, I have a Three Stooges slide on that. So yeah, I hired Bill Murray from Caddyshack to ram the system through the window of my lab when we first installed it. And this is what it looks like. We have it so covered in lead that we're able to be just across the other side of the lab while we collect data. It's nice not to have to be in a different room and get a better view here. These are the X-ray sources that are just encased in lead tubes. You see the horizontal and vertical. Unlike the ground systems, these are fixed on the horizontal and vertical axis. And opposite these sources, we have the image intensifiers, the large format 16-inch intensifiers. And almost all the experiments in my lab use some kind of force sensing techniques integrated with the 3D X-rays. And these are 6-axis load cells from AMTI with carbon fiber top plates fitted, so the X-rays can go right through them. We can get the forces with a good natural frequency.
So you get forces over shear as well?
Yeah. Yeah, so we can't, so see, these are industrial sources. We can't get away with doing anything human, of course, because it's not, as Robert mentioned, this is not a pulsed X-ray source, it's a continuous X-ray source. And it's regarded as just too dangerous. So a lot of the experiments in my lab, and I want to just make this point clear, that XROM is not equivalent to X-ray motion analysis. And as we know, we can do an awful lot with motion analysis without going that extra step to make the really beautiful 3D reconstruction of basically registering that 3D bone, a 3D rigid element back into the kinematic space. This is like a sort of proverbial stick model of the system. XROM puts the real bone back in the system. I just want to make that distinction clear. So we've got some one of the main topics in my lab. We're looking at guinea pigs as a model for human spontaneous knee arthritis. And these are just two views of guinea pig running over an array of those force plates I showed you. And I'll spare you the details here. But we're looking for mechanical events that may predispose a joint to arthritis. And we use platinum markers, sometimes also tantalum. Platinum is twice as dense as lead, so that's when you look at metals, the denser it is, the better contrast you can get with the tissue of the animal. And the other thing to point out, so within this X-ray motion analysis, there are kind of two different ways to approach it. You can either look at each segment as an isolated unit, as an isolated rigid body, and that's what we're doing in the case of these guinea pigs. The main point is we don't know how the knee joint is constrained. What we want to do is study in 6 degrees of freedom, rotation and translation, the mobility, the impedance of that joint. So it wouldn't make sense for us to make assumptions about the constraints of the knee joint, so we analyze the femur and the tibia separately in this particular study. But there are other studies that are certainly conducive to, this is work by Ted and Kit and from Keith's lab and Benjamin Giles, where the approach is to, instead of looking at each segment individually, spreading the markers out over the multiple segments of the leg, and then building a linked segment model of the whole leg that's not unlike human inverse kinematics, where we can actually just snap the entire leg to a collection of fewer markers that so it kind of cuts down on the invasiveness of the surgical approach. We also just look at the Harvard system. It's a C-arm system, also 2 axes. It's hummingbird flying away there, very much slowed down. But I didn't really point out early on. But the real value, especially for comparative biomechanics, is we've for decades we've been dealing with movement of muscle and skin and fur and feathers, and that's part of the problem. That's part of the reason we need X-ray motion analysis. And also, the problem is much intensified at proximal joints, so we know a lot more about distal joints more accurately than we know things about proximal joints. Also, other things that we work on, things like terrestrial crabs right now. It's been hard historically to get kinematics of the segments of the crab because we're looking at 8 legs moving around, always including each other. With X-ray, we can see straight through. And I've got a graduate student right now, Lexi Moore, looking at burrowing of gophers and South American versions of gophers that we couldn't obviously see something burrowing through soil without X-rays. So with that, I want to say just a few things about force sensing. We've actually, on the guinea pig project, we moved on to a force sensing elliptical machine for guinea pigs, but using the same load cells. It's because the guinea pigs won't run, and they especially won't run as they get more arthritic. So we put them on elliptical machines where we can actually control the oscillations of the foot. I have a picture on the poster. It's not in here though. I think they're gonna sell like hotcakes actually. So 6-axis load cells. It's important, of course, to do all you can to isolate from the vibrations of the whole system, isolate the load cells from the vibrations of the system. We mount them to heavy steel plates, and then we've got layers of lead, which is a really nice damper between the aluminum structure and the plates the separate steel plates that support each of these load cells. The lead acts as a dissipating part. Yeah, and multiple. You get better damping with more layers you have, the more kind of those contact zones you have, the better damping you can get as well. So layers of lead under this do a nice job. And they also block X-rays, so it's healthy for everybody in lab. Some unfiltered force data from the system, so it's not. Carbon. X-rays go right through the carbon, so it's good. It's also quite stiff. The tops of these. This is just a 6-axis load cell. We turn it into a force plate by cantilevering this carbon top plate off of it. So some basic considerations. Of course, we have to know where that force plate is, where the sensing center of that force plate is in the 3D coordinates of the X-ray motion analysis. So that kind of goes without saying. Same sort of things we deal with in human stuff. I'm going to say just a few other things. The methods that we use to get details about 3D structure that can either contribute to X-ROM or help us kind of estimate some of the geometrical and inertial properties in order to do segment dynamics. Our computed tomography, micro CT, which is a little harder to find. Sometimes I don't know who anybody's actually used MRI, but that's one way. And then we also, for the crabs with the exoskeleton cuticle, we use laser scanning to get the geometries. This is just a regular old medical CT. We removed a bunch of artifacts, and you can see the high density, tiny little platinum sphere. It's only about 0.5 millimeters diameter. We're able to spot them there. And it's important to know, even if you're not doing X-ROM, and you're building a link segment model, it's important to know where your markers that you see in your actual experimental data are with respect to, if you're doing link segment approach, you put some joint constraint. Of course, you need to know where your joint constraint is in space with respect to the markers on the bones.
So why is there no more?
This is an early pilot. This is a rabbit cadaver went through some markers and to test
Okay,
those.
just
Yeah. This is the Harvard, probably the nicest micro CT in the country. Detail you can get on a rabbit skeleton. Some other groups, some vet groups have actually used CT data because CT will give us a picture of the soft tissue as well. You can make some assumptions about the density, physical density of muscle, bone, and actually it's one sort of alternative way of estimating inertial properties of a segment that doesn't involve kind of hacking off a little tiny segment and trying to swing it around or something like that. So that's something that we're exploring in 3D. So we get mass, the center mass, and an inertia tensor there. And the X-ROM you've heard all about. Of course, I'm not going to talk about it. And I just want to say a few more things about dynamics and maybe get some of your feedback or insights on dynamics. I'm not wildly experienced with sort of these the really detailed inverse dynamics approaches that are so common in human work, and so we've had to make some of our own solutions. And Craig McGowan is a collaborator from the University of Idaho who's actually done lots of forward dynamics from Neptune's lab, so he's working with us on it now. But the two basic, if you're doing a link segment model, you've got the inverse kinematic step where you've got to take your stick figure and snap it to your experimental data somehow, minimizing the overall error. And if you're using either X-ROM or just doing X-ray motion analysis on a segment like we are in the guinea pig on the femur and tibia, segment by segment, you don't really need to worry about this because you don't have a link segment model to snap into the data. So it's only when you're looking at the leg as a whole that you do this step. And of course, when you do inverse dynamics, you need to think about the inertial forces of the segments swinging around. Guinea pig elliptical machine is actually slow enough. We don't worry about the inverse dynamics in that case. There's actually no swing phase, just a slow back and forth motion. It's important also to point out that inverse dynamics gets us sort of a net applied force and torque at the joint. It doesn't tell us the contact forces at the joint, and some people sort of assume it's a silver bullet for everything. And you need to have a really excellent forward dynamic model that includes the possible co-contraction of flexor and extensor systems before you could really know what's going on with contact forces at the joint. So this approach just gets us sort of, I sometimes call it kind of characterizes the loading environment of the joint or the applied loads at the joint. It's not explicit in the way that sometimes we're led to believe. And also, really powerful. Tom is forging ahead with the tracking and muscle tendon structures. I wanted to add to that sound micrometry is a 1D sort of explanation of what's going on. But when you get when you're using the X-ray techniques, you're getting a 3D look at the muscle. So you're getting a lot more information to see how those markers are moving with respect to each other in 3D and with respect to the bones and the joints. So it's got a lot of promise, and I'm excited about that, and combining it with the other dynamics. So just quickly summarize, and looks like everybody's about done with the meeting. But the X-ray motion analysis lets us really look at small animals, more proximal joints, animals that have a lot of occlusion between the segments, and actually start to look at the spine and other structures that are pretty hard to visualize. It's in a lot of the things we need to do X-ROM are also things that are useful for doing dynamics. So we like to see sort of an overall approach where we can tie these things together and sort of realize the usefulness of the basic data we're getting. And I think that's all I've got.
One thing. So the schedule is you're on your own for lunch. There's some restaurants in the hotel. Also across the street to the right there, so from a strip mall that has a few faster places possibly. And we'll start up at 1:30 with Russ Tendrick's tutorial B. There's an email around about installing some software from MATLAB and some other auxiliary code to get ready for that tutorial. Do you have any questions?
I do. Has anybody done it? How long does it take?
It doesn't take long.